Hello and welcome to another video. In this video we're going to be doing the last problem of the weekly contest 36, which is the earliest second to mark indices 2. And this is going to be kind of similar to the first one, so I definitely recommend doing the first one as this is like a harder version of that with different things you have to do, but the concept of how to solve it is similar. So you're given two one-indexed arrays, nums and change indices, just like in the problem before, having lengths n and m. Initially all indices are unmarked. Your task is to mark all indices and nums. In 1 second, you can perform the following operations. So this operation is the same as the previous problem. You can choose any index and decrement it by 1. This is the different one now, is you can take this current index you're on and make it non-negative, where before you could mark it. And now you can mark any index you want at any time. So you can mark any index you want at any time. You can decrement any index you want at any time, but you can only do this like this operation here whenever the index is in the change indices. Or you could do nothing just like before. Return an index denoting the earliest second where all the indices and nums can be marked, or -1 if it's impossible. So they kind of show you this first example. So in this first example, they said in the second one, you want to change num indices 1 to 0. So you have this. In second 2, you can change num indices 2 to 0. Yeah. I guess this is actually not num indices 2 to 0. This is going to be this index over here. So at first second, you turn this 3 into a 0 because this is a 1. Second one, you turn this into a 0 because of the 3. These are 1 indexed. And then finally, in the third second, let's see here actually. Yeah, so in the third second, you turn this to 0. So because you have 1, 3, 2, in these first 3 seconds, you can use this operation. So this is kind of like a hint. So whenever you can change the num indices to a non-negative value, you basically always just want to change it to 0, right? So if you're allowed to change index 1 over here, you just want to turn it into a 0 because everything 0 can be marked. So that's kind of obvious. So in the first 3 seconds, you're going to turn all these 3 things to 0, and then you need 3 more seconds to mark these 3 things, and you can mark any index at any time as long as it's 0, regardless of what these are. So it takes 6 seconds here. So let's go on the second example. So in the first thing, you can, let's see here. In the first second, you can mark index 1, so we'll mark it. In the second thing, we can mark index 2. And then index 3 and 4 are never in here, so you have to decrement these manually. So to decrement all of these total takes 3 seconds, and then you have to mark them as well. So marking overall takes 4 seconds, and decrementing these takes 3 seconds, so you have 7 total. In the third example, you can like make these 0, but you don't have enough time to mark them, right? Like even if all these indices exist, which they do, in order to make them 0 and mark, to make a number go from something to 0 takes 1 second, and then you also have to mark it, which takes another second. So you would need 6 seconds for this to work, and you don't have that. So there's no way to do this one. Yeah. And so let's go over like how we would do this and how this is similar to the other problem. So they do kind of like tell you, like they do hint for you that this, whenever you do want to use this operation, you want to just make a number 0. And it's pretty obvious that like you want to use this operation as much as possible, right? So when we have numbers and nums, ideally we make them all 0 using these operations, right? So the index is in this change indices and we use it and we make the number 0. But there's like, we're not always able to use it, right? So let's look at an example. So let's say this is our nums and this is our change indices. So you can't always use this operation. And a really clear example of that is this one right here. So for example, here, in this change indices, at second 9, you can make this 0. But if you do that, you don't have time to mark it, right? Like if I use this operation to make this 0, I can't mark it because I don't have anything available afterwards. So basically, like you can see that like if this occurs here and if there's a 4, like let's say this was a 4, right? You can see how it would be better to use the operation here to make this 0 instead of here, because if this occurs twice, you want to use it earlier because that gives you time to mark it afterwards.
And if you did make it 0 here, like there's nothing else you can. Well, there are things you can do here, right? There are things that, like if we look at other operations, what else can we do, right? Like we can mark. So let's go back to this one. So we can mark at any time, and we can also decrease by 1 at any time, right? But we can do these things. We can do these things later on. So basically, you kind of have to come up with the fact that whenever a number occurs multiple times, the best time to use the operation is right away, because then you have time to do other things. So kind of like in the other problem, you knew that like if you were trying to see is this possible, like that's kind of the problem we're trying to solve again. We're trying to solve like given this, let's just see if this is possible. And if this is possible, then we know how to like make it fast enough with a binary search like in the problem before. So we could say like given this nums and this change indices, is this possible? You know, if we can answer this problem, then we can binary search other indices to figure out if that's possible as well. So that's kind of the main thing, is if a number occurs multiple times, the best time to mark it is right away, because then we have time to do other things. And if we mark it earlier, sorry, not mark it, the best time to decrease it to 0 is right away, right? So if a 4 occurs here or 4 occurs here, you can clearly see an example here where if you tried to make it 0 here, this is going to be better than here, because here it's not going to work, right? And that's the main idea of this problem. So now the other part, like once you figure that out, that whenever you have a number occur multiple times, you want to just mark it. You want to just decrease it to 0 at the very first occurrence. So what we can actually do is we can just make a hash map of every number and its first occurrence. So we could say like, okay, well, index 1, its first occurrence is at 0, right? Index 2, its first occurrence is at 6. Index 3, its first occurrence is at 8. And index 4, its first occurrence is at 9. And then we can kind of do a similar thing that we did in the problem before, where we will only decrease to 0 at these times, right? We will only decrease at 0 at these times. So we're going to try to, if we are going to use this decrease to 0, we're going to use it here, 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 and here. Now the thing is, like I said, even though you know when to do it, you still won't necessarily be able to do all of them, right? Like in this one, obviously you can't decrease this to 0. You can't use that operation because you still have to mark the 4 afterwards, and you have no time. So you're gonna have you need, before actually like making it 0, you need to figure out like, do I have time? So we can write this down. So before using decrease to 0 operation, figure out, do I have time to mark it, right? Like, and if I have to figure out, like, if I do decrease to 0, figure out, do I have time to mark it? So in order to decrease to 0 and to mark something, that takes 2 seconds, right? So basically the way we're going to do this is we're going to go backwards. And the reason we're going to go backwards is because for every single number, we need to figure out, like, do we have time after that number to do other things? So we're going to keep track of all of our available time. And then we're going to keep track of, basically, we're going to separate our problem into two categories. We're going to separate our problems into all numbers we can perform decrease to 0 on, and the rest. And then all numbers we can perform decrease to 0 on, it's going to be very easy to figure out how long it takes to do that and to mark it, right? So like I said, to decrease a number to 0 using this operation over here, this one, right, is going to be 1 second to decrease to 0 and then 1 second to mark it. So for each of these, it takes 2 seconds to decrease to 0 and mark. So if there's like 6 numbers here, it's going to take 6 seconds to decrease them to 0 and then 6 more seconds to mark them. And then the rest, the way this is going to work is we can just pre-compute how long it takes to do everything. So that's the thing. So let's assume we don't have this like array. Let's say we can't decrease anything to 0. How long does it take to manually decrease every number to 0 and to mark every single number, right? Like every number, we just decrease by 1 at a time. Well, that's just going to be the sum of nums, right? Because every number, you have to decrease it to 0. You decrease it 1 at a time. So to decrease this to 0 manually takes 106 seconds. And to mark every single number is just the length of nums, right? So this is just sum of nums and length of nums. So if we never use the shortcut operation decrease to 0, this will be the answer of how much time we need to make everything 0, right? And so this is going to be like the worst case, basically. And then the best case is for every number, we can use the operation and we can mark it in 1 second, right? So that would be just 2 times length of nums, right? For every single number, we can just decrease to 0 in one operation, and then we can mark it. And so the answer is going to be somewhere in this range, basically, right? Like you know, if you have this, you know, if you have this time, it's always doable. You know, if you have this time, if you have less than this time, it's never doable, basically, right? Well, actually, sorry. Actually, let me take that back. So I think this might not be 2 length of nums. It's actually being length of nums, because imagine every number starts off as 0. So if every number starts off as 0, then you don't need to decrease it to 0. You just need to mark it, which will be length nums. But your result will be somewhere in here. So then the next thing we're going to do is, if we choose the 0 operation on the number, we're going to figure out like how much that saves us. So let's figure out, first of all, like what's the brute force for this. So the brute force for this is 110, right? Because we have to decrease everything to 0, which is the sum, which is 106. And then we have to mark each number, which takes 4. So it's 110. Then if we use the shortcut here, we're going to treat the shortcut as like a separate thing. And I'll kind of show you how that works there. But essentially what's going to happen is anytime we use the shortcut, we're just going to get rid of that operation. So what we want to really save is how much more time we need for everything that we're not using the shortcut for. So if we use a shortcut for 100, for example, what are we saving? So instead of like this took 100 operations to make it go down to 0 and 1 operation to mark it. So we're saving 101 operations. I'll show you why the marking works the way it is. So basically we need 9 to do everything else, which is correct, right? We need 6 to make these all go to 0 and then 3 more to mark it. That's kind of the idea, is we're gonna calculate how long it takes to turn everything to 0 that we haven't used the shortcut on. And then we're gonna have to figure out like, well, how much available time do we have left after doing all the shortcut stuff? And then if our available time is greater than or equal to however much we need to turn everything else to 0, then we've kind of succeeded. So let's walk through how this is going to work. And also, like I said, you're not always going to be able to, so there's one more trick. You're not always going to be able to you're not always going to be able to like turn things to 0. And sometimes you have to choose between 2 items. Like sometimes you'll only be able to fit one or two one out of 2 items. And in that case, you basically, like, if you think about it, if you can only fit 1 operation to turn to 0, which one would you rather pick, right? If you can only pick one of two different ones, well, you'd always want to just turn the thing to 0 that takes more operations to turn to 0. So the way this is going to work is we're going to use a heap to keep track of like what are all the things we can turn to 0, and we're going to try to fit as much as possible. So if we do have the space, we're going to fit in as much as possible. But if we don't, if we have to pick, we're going to pick the items with the highest like total to put in here, because those take the most operations to turn to 0. So those are the most important ones to use the shortcut on. So now that we have that, let's walk through how this is going to work. Remember, we're going to go backwards. So first we get the index of like the first occurrence of each index, because we discussed that if something occurs in multiple places, it's better to use the operation in the beginning, because then you have time to mark it. So yeah, so let's walk through how this will work. So in here, we basically have to keep track of a couple variables. So I made a variable called available space, which is just available operations we have. So over here, we don't have any available operations. We're going to be counting from the back. So available operations means like how many available operations do we have after this one. So in the beginning, it's 0. So that's why we can't use this decrement operation here, because we don't have time to mark it. So in order to put this into the heap, to make like all items in the heap will be the things that we're using the shortcut on. So in order to put this into the heap, we have to have available time to mark it. We don't. Or we have to have something in the heap we can swap it out with. But we have an empty heap and we have no available time. So we can't use a shortcut here. So here, we're not going to use a shortcut.
So, and then we're going to go to the element before that. So here we're not going to do anything. Now that we go to the element before, now we do have one available second, because here, like if we choose to do something here, we do have the one available second afterwards to do something, right? Available is literally just going to mean time to do anything other than the shortcut and marking the shortcut. So here, now for this one, we can make it go down to 0. And this is also the first time it occurs, right? So 8 is the first time something occurs, 9 is the first time something occurs, 6 is the first time something occurs, and 1 is the first time, or 0 is the first time something occurs. So these are the only times we're going to be using this like decrease to 0. And here we can use this decrease to 0 operation on the 3. So if we use the decrease to 0 operation on the 3, we're going to put into the heap. So we're going to say we're going to use it on the 3, right? Or it's going to be the item at index 3, which is 2. So we're going to put it into the heap. Yeah. We also need to, so actually what we need to do is we need to store the like index of the item, and we also need to store the item. Maybe you can just store the item. Maybe that'll work, but I think in my code I ended up storing the index and the item. So remember, we want to store the index and the item, or maybe, like I said, maybe just the item will work, because we want to have our heap have the biggest things possible if we have to make a choice, right? We want to use operation on the biggest things possible, because everything else will take less operations. So we're going to put in the number itself, which is for 3, it's 2, and then the index is 3, one indexed. That way, when we run into something else later, we'll have a choice. Okay. So now we're gonna, and let's think about it. So if we put this into the heap, to make this to make this go down to 0 takes one operation, and then to mark it takes another operation. So we had one available operation, but putting something into the heap actually takes 2 operations, right? Because we have to make it go down to 0 and mark it. So now we actually have 0 available slots. And because we chose to use the shortcut on this thing, right, we're going to take our total sum that we had before, which is 110, which is like brute force everything. And we're going to figure out, okay, how much is there left after we use the shortcut and mark it. So if we use the shortcut and mark it, using the shortcut here will get rid of 2 operations, right? And then marking it will get rid of another one. So this is -3. So we need another 107, right? Like if this is done, then we need 107, because this is 100, 102, 104, and then 3 things to mark, so 107. Okay. Now we're going to come over here, and we're going to say, okay, so do we have available space? No, we don't. But can we swap this out with something in our heap? Well, this is the same count as this, right? So it doesn't really matter like which one. Like you can only use the shortcut operation. Or actually, sorry, we're not going to be doing anything here because this is not the first time it occurs, right? That's also why I said it's better to do it here, because here you can only pick one of them, but you can just do it here instead. That's like another thing you can see why like it's always better to do at the start. So here, because this is not the start index of a number, we're not going to ever put it into the heap. We're just going to mark available operation, right? So here's an available operation we can do. And this makes sense, right? So here we can do whatever we want. Here we're going to put 3 into the heap, and then here we're going to mark 3. So we have one available operation. Okay, now we go left. Okay, so now we do actually have just the spot to put this into the heap directly, right? Because we have one spot. If we come over here, we actually have 2 spots. So we can say like, let's put this into, let's make this 0, then let's mark it, then let's make this 0, and then let's mark it, right? We have 4 slots to be able to do this operation. So using these 4 slots, we can turn this to 0, mark it, turn this to 0, mark it. Or not that one, this one. So we can put that into the heap. So this is going to be number 2 with index 2. That's our heap. And now our available space is 0, which makes sense, right? Because it takes 2 operations to turn something to 0 and mark it as well. Oops. Okay, I'm just going to leave it the way it is. This is now crossed out, right? Because, this is basically, these 2 are going to be the things we're going to be using the shortcut on. Now we're going to go over here. And we're going to say this is not the start of a 1. So if anything, we wanted to make the 1 into 0 here. So this just gives us available space.
So now we have one available space. And then I'm going to kind of fast forward through this. So we have one available space. Here we'll have two available space, 3, 4, 5. Now we come over here. So we have 5 available space. Now here, we can just put this in, like, we can just put this in, right? So basically, we can say, okay, well, let's put this in. So, yeah. So we can put this in and we don't have to like replace anything because we have enough available space to just put this in directly. So we can say, okay, let's put it in our heap. And this is going to be at 100. And this is going to be 1. Then we can get rid of this. Okay. And yeah. And then, oh, I forgot to decrement here. So by the way, so when we put this in, our available space will go down 1. Right. So every time we put something in, our available space will go down. If we don't put something in, our available space will go up. And if we swap, our available space will also go up. So because we used all these 3 things with a shortcut, so this one will save us 101 operations. So minus 101, we have 6. And then we forgot one of these, which saves us another 3 operations. So now whatever we have left, like this is the only thing we have left. And this takes us 3 operations, right? Like, and we can easily figure out where those are. We don't really care where those are, but we can kind of see that, right? So like, let's say here we turn this into a 0 and we mark it, right? That's 1, so that's done. Then here we turn the 2 into a 0 and we mark it. Then here we turn the 3 into a 0 and we mark it. Then we have all these cells, right? These 4 cells to do anything we want with a 4. So during this time, we can just make the 4 go down to 0 manually and mark it. And yeah. And then we just check at the very end, like, okay, what's the available space that I have after I did this? I had 4 cells to do whatever I wanted. And then what are the operations I had left, which is 3. And because 4 is greater than 3, then you can say this is possible. So let's cut down a few cells and show like when it wouldn't be possible. Let's try that. Let's see if it wouldn't be possible if we just make this a little bit shorter. So let's keep this. Let's keep all of this. Let's get rid of all of this, and then we will just basically do this again, but let's cut down some cells. So, I don't know if I can delete this stuff. It's gonna be kind of hard. I guess I can. Kind of hard to click on. Maybe not. Okay, so let's just get rid of this, and let's see if this is doable still, right? So let's go back and let's try it again. So remember in the beginning, and then we'll have our available cells again. So remember in the beginning, we're gonna have like all the indices that we want to be using the operation on. This is still going to be the same things. Now this 4 doesn't exist, so we'll get rid of that, right? Because there's no 9, so it'll be like this. So the indices we want to do operations is here, here, and here. Okay. So in the first index, like this is the index you want to do an operation on, but like I said, we can't do it. We can't make this go down to 0 in one operation because there's no space afterwards to mark it, right? So we can't put it in the heap. We can't use this operation. We can't take it. So we'll just mark we have 1 available cell. Then over here, like I said, or if you're going to take this operation, it's always going to be better to do it here because then you have time to mark it. You have more time than before. So here we're doing nothing. We're just going to mark available into 2. And we'll start with a sum of 110 again. Then we'll come over here and we're going to say, okay, so this is now we do want to do this like shortcut. So if we do the shortcut, we're going to save ourselves 3 operations, or this is like how much we have left, not save, but this is how much we have left. We have 107 left. Put this into the heap. So we have 2 and 2. And now how many available cells do we have? Remember, if we put something into the heap, we take our old number and we subtract 1. So now we have 1 left, which makes sense, right? Because you need 1 operation to turn it to 0 with a shortcut. You need 1 operation to mark it. You have 1 left. Okay, now we're going to speed this up. So we're going to say we have 1 more available cell here, another one. So 2, 3, 4, 5, 6, 6. Okay. So we have 6 available cells, right? And let's just double check that.
So this is going to be basically taken, or like this is going to be basically taken. Some of these are going to be taken. This is going to turn to 0. One more to mark. Then we have 1, 2, 3, 4, 5, 6. Now we're on this one. So that's correct. So we have 6 available cells. Now we're going to use a shortcut here, right? Because we can. So this 100 will now be put into the heap. I haven't really shown a heap replacement, but that's okay. The idea is basically just whenever you don't have available cells and you have something in your heap, if you're trying to put something in instead, just check. Is that number bigger than the smallest element in the heap? If it is, do a replacement and then modify the sum, right? So for example, if you had a 2 and you're putting in 100, you would do a replacement. And now how many operations are you saving? So basically the difference here, right? So you're saving another 98 instead of 100. So yeah, so then you just like subtract 98. So I'll show that in the code as well. Anyway, so this is like this. Then we subtract 103. Or not 103, 101. It takes 101 total. We have 6 operations left, which is correct, right? So we did the shortcut here. We did the shortcut here. These take 2 each to make down to 0, and then 2 more to mark. So now we can check, and because we put something new in the heap, our available cells is 5. So we have 5 available cells. We need 6. So this wouldn't be doable. And you can kind of see, like, it's pretty easy to figure out the optimal scenario here, right? Yeah, you want to make this a 0 at one point because it's 100. So let's say we make it a 0 here. It doesn't really matter where. Then the next one you mark it. Then we have 4 operations. So in these 4 operations, we can turn these items into 0, let's say. So we turn that into 0. Then we use a shortcut to make this into 0. Then we basically, now we can mark whatever we want because everything's 0, but we only have 2 mark operations and we need 3. So we can mark like 2 of them, but we don't have enough for the third one. So that's kind of the idea. So I think that's enough for the code, and let's go through the, or not the code, but the drawings. So let's go through the code. So binary search, just like previous problem, where basically you just solve an instance of this problem, right? So that's another thing I forgot to mention. So if we have this array, we just try like different end indices, and then it takes O of M to see if it's solvable, right? So if this is length M, it takes O of M to see if it's solvable, give them some index, and then you can binary search all indices, so it'll be like M log M. And yeah, so we just binary search starting from, like I said, the least number of numbers. It's not really going to change time complexity too much, but you're never going to be able to like this is never going to be viable. The least number of indices you need is at least length nums, right? Because even if nums is all 0, it's still going to take like length nums operations to mark everything, because it takes 1 operation to mark everything. If you want to be a little bit more accurate, you can check for non-zero numbers in nums. So you can be like, okay, let's say there's like 100 non-zero numbers in nums. Then you know it's going to be 100 plus length nums. I didn't bother doing that, but you can do that if you want. It's not really going to make a difference in binary search. You can also start this with 0. It's all honestly not going to make a difference. Then, like I said, we make a total operations. We need to make everything 0. This is something we are going to use, and that's just the sum of every number in nums plus the length nums, because we have to mark everything, which is length nums, and we have to turn everything to 0 brute force, which is sum nums. Then we just have like our result index that we try things on, and then I made this helper function just like before. Can we finish at this time? So I made a copy of the total, and then I made a dictionary of the first occurrence of every single item, just like we did here, right? Because we determined that you want to just mark the leftmost item if you have to pick. So we just go through it. We just get the first occurrence of every single item. We make a heap, and then we make this like available that I was talking about. Then we go through our indices, and we just check if our index is in the first indices, and if we do have available space, push it into the heap and decrease available by 1, and decrease the current total by the number of the number plus another one for the mark, right? So we treat basically everything we do in the heap separately from the rest. So everything in the heap, the amount of operations you save is the value of the number plus 1 more for marking it. So we decrement our current total appropriately. Otherwise, if we don't have available operations, but we do have elements in the heap, and our current number is bigger than the smallest item in the heap, we're going to say this is a better
number to use a shortcut on. So instead of using the shortcut on some smaller number, we'll use it on this because this saves us more operations, right? Because ideally we want to decrease the current total as much as possible and increase available space as much as possible. So this will increase our current total for us. So that's the case. And if we do a swap, so I didn't talk about that. If we do a swap, we do have one more available slot because like your current total changes, but if you do a swap, the reason available goes down if you put in a brand new item is because you have to make it go down to 0 and mark it. But if you do a swap, you're taking out an item and putting in an item, so it's the same amount of time to like make it go down to 0 and mark it using the shortcut, right? Like if you're taking out like 2 and putting in 100, well, it takes one operation to make 2 go down to 0 and then one operation to mark it. It also takes one operation to make 100 go down to 0 and one operation to mark it. So if you do a swap, your available space still increases because you do have that one extra index now that you're on. Otherwise, if this is not like in the first index, then you're never going to want to do the 0 operation, right? We're only doing the 0 operation at the first occurrence of an item. So otherwise, just increment the available slot. And then at the very end, just check, is my amount of available space to do everything, not including my heap operations, greater than or equal to the total of everything other than my heap operations. And then you just do a basic binary search where you just start at the leftmost, or yeah, like at this index and this index, and just return the leftmost index where this is possible. So this is just a basic like time, like, because I think I talked about this before, like let's say this at this index, this is true, like let's say it's possible here. Well, if it's possible here, then you're never going to want to check any of these. You just mark this location and then you check this in your binary search, right? Because like it's possible here, but you want the least time that it's possible. And if it's false, so if we tried here and this doesn't work, then we know it doesn't work here out of 2 because the pattern's always going to be like, it's going to be false to the left of every false value and it's going to be true to the right of every true value. So if this false here, we just get rid of all this and then we check this. Does any one of these work? And if we don't find anything, then we can just return -1. So we can run this. Yeah, it's pretty fast. And the time complexity is also a little bit easier for this one to figure out because I think it's a lot more straightforward because we're not doing like any shortcuts or anything. So the time here, basically, so we're binary searching through the, I renamed this to C. I think this was called like check index or something. Let's see. So it's called change index. So let's call that like C or something. So it's going to be basically C log C because we're just picking indices in the C array, and then we are going through that whole subarray. We're going through it left to right and then right to left, but that's still O of C. And yeah, and we're doing like heap pops and stuff, but that's not, actually, will that change it? Actually, I think that will change it. Yeah. Yeah, because for every single index, you might have to do like a heap push and a heap pop. So I think actually it will be more like C log C or something. So it'll be like C log squared of C, because like you might have to do like heap pushes and heap pops at almost every single index. So that would, but that's still like easily gonna pass because like something like that. And in practice, it's gonna be a lot smaller. Obviously, as you saw, it was pretty fast. As far as the space, so let's take a look. So we do mark the first occurrence of every number, which is going to be obviously O of num, so we can call that like O of n or something. And the heap will also be O of n, right? Because we're only storing each number once at most. Yeah, so because we're only storing each number once at most, I think it's just going to be O of n space. And yeah, so I think that's going to be a pretty tough problem, pretty hard to come up with the greedy stuff for sure. But I think once you've done like the first problem, you kind of realize like, okay, if I can just get like one check to work, then I can binary search through the rest of it to figure out the rest. So definitely solving the first one makes this one easier. And it's kind of rare because usually like this is very similar to the first one. I originally thought they were literally the same, it's just a tougher constraint, but they're actually like a not completely different problem, but kind of different. But yeah, anyway, so if this is helpful for you, please like the video and subscribe to the channel.
and I'll see you in the next one. Thanks for watching.